Good afternoon and welcome to the accompanying presentation to my ELRC 7503 Instructional Design project from Fall 2 2021. This is on the topic of optical isomerism. So the agenda for today's presentation, firstly we'll cover a very quick overview, and then we'll go through the synopsis of the programme, so the learning objectives, assessments, materials and strategies, the rationale of the design and a reflection on the project design and development process. So this instructional design project is on optical isomerism, and it is for a 1-week course following the AQA A-Level Chemistry specification for the optical isomerism chapter. In the UK, there are many different specifications we can use for A-level chemistry, ranging from AQA, OCR, Edexcel, and Cambridge Internationals and WJC. However, I'm going to use AQA for this one just because it's a very common one to use. And why this chapter specifically? So optical isomerism is actually a great starting point to start collaborating all your information together. There are some aspects of the content that have been visited before in prior chapters, such as mechanisms in organic chemistry, but also isomerism in GCSE. And from the skills gained from this chapter, these skills can be easily applied to the future chapters. So if we can get this chapter top notch, it's very, very useful moving forward in A-levels. And here are the participants. So the participants in this course will be for A-level students, so this will be ranging from 16 to 18 years old, and they would have previously have taken GCSE chemistry, so the end of secondary school exam, and to be allowed onto the course in general in the UK to study A-level chemistry. Normally students will have received a grade 6 or above, which is the equivalent of a B. So all students will have a strong prior knowledge of chemistry, and due to the national curriculum, they will all have the same prior knowledge, and that's very useful for A-levels moving forward. So next I'll discuss the rationale of my design. So this course is designed to be asynchronous. I'm very understanding that students are very busy, and I think asynchronous works the most effective as long as there is ample opportunities for student-instructor communications, which there will be. And next, this course will be uploaded to a Moodle structure, and it will also be very interactive with different technology tools, and if there are any paid ones, free alternatives will be provided. Now, the design of this course, I have used the backward design model, and this was originally designed by Grant Wiggins and Jay Matayek, and it's a model for designing instructional materials where the instructor or designer begins the design process with the focus on the desired results of instruction. For example, for this one, I will start with devising the learning objectives, then assessment, materials, strategy, and then the content itself. After exploring many different various instructional design models in LRC 7503, such as the ADDIE model, for instance, I still found the backward design model most suited to this optical isomerism instructional design project, and that is why this was selected. So now I'm going to discuss a quick synopsis of the programme. So on the slide here, I actually have the contents that students will learn. So firstly, we'll go with the prior knowledge of isomerism. So this is the type of isomerism they would have learnt at GCSE, but also prior chapters in organic chemistry. So this ranges from functional group isomerism to chain isomerism. And next we will go into an introduction to optical isomerism. So this is learning our key definitions and models, but also how we illustrate and draw optical isomers. Next, we will learn optical isomerism and how it is used in the pharmaceutical industry. And this chapter is very interesting because there's a lot of ethics involved, and it's also an opportunity to go and practice our long answer questions. And finally, it will be a consolidation of optical isomerism, where we'll use all the content of our previous lessons in the course, but also prior knowledge from other chapters in A-level chemistry, so mostly organic mechanisms and balancing equations, which would be really, really useful. So to devise our learning objectives, I will be following the revised Bloom's taxonomy from 2001. And this is a framework for categorising educational goals applied by educators like myself. And it consists of 6 major categories: remembering, understanding, applying, analysing, evaluating and creating. And with these, I can use it to establish the learning goals in my programme, and it can help organise the objectives simply for us and for the students. So using Bloom's taxonomy, I came up with 4 learning objectives for this course. The first one is remember, and this taxonomy level is a very low thinking order objective. And here students will be able to recite the definitions of chain, position and functional group isomerism. Next we will cover the application taxonomy level, and students will be able to sketch 2 variations of optically active enantiomers. Next, evaluate. Students will be able to evaluate the effect the thalidomide disaster had on the pharmaceutical industry and why it became a tragedy. And finally, we will go on to the create taxonomy level, and this is a very high order and a lot of thinking skills involved, which will really help the students to critically engage their brains. And here, students will be able to formulate a reaction between 2 reagents to determine the 2 enantiomers produced from the racemic mixture. And from there, they will also be balancing equations and using organic chemistry mechanisms. And from the learning objectives, I then devised 4 assessments, one for each learning objective. And for the first learning objective, students will be given a worksheet where they will have to recite the definitions of chain, positional and functional isomerism. And the reason why they will be reciting these definitions is because in A-level chemistry it's very frequent that students will have to memorise definitions, and these will appear in the exam at the end of the course every 2 years. And from the practice of recitation, it makes it a lot more easier for students to apply this moving forward with more definitions. For learning objective 2, the students will be able to complete a series of 3 sketches of various optically active enantiomers, and these will vary in difficulty. These will be assessed formatively in the style of an exit ticket at the end of the topic before progressing to the next topic, and these will also be self-assessed by the students. Next, for learning objective 3, the students will provide and create a written paper, and they'll do this by following an analytical rubric, and this will be similar to the mark schemes provided in the AQA examinations, and these will be used to determine their understanding on optical isomerism and racemic mixtures. The question posed to the students will actually be, using your knowledge of optical isomerism, evaluate the failings of the pharmaceutical industry in regards to the thalidomide tragedy in the 1950s to 60s. And finally, for learning objective 4 for the create level, following a checklist rubric to help the students will compile all their knowledge from the course into an end of course assessment, which will form one long answer question. And this question is to formulate a reaction between ethanol and hydrogen cyanide, and from this include the word equation, balance symbol equation, mechanism and sketches of the 2 enantiomers produced. Throughout the course, each learning objective will have the accompanying learning materials. Each objective will have a lecture provided by the instructor, which will include many teaching models. We will have cartoons, recorded Zoom lectures and different multimedia throughout. For example, there will be a short clip from Call the Midwife. And next we have the learning strategies. In this course there will be 2 that I will cover, and that is retrieval practice and inquiry-based learning. And retrieval practice involves the use of recurring testing over a period of time to encourage the students to recall material from memory. And it is found that the use of retrieval practice actually enriches students' learning and retention of material. As I said before, these definitions questions are very, very frequent in exams, so the more practice the better, and retrieval practice is an excellent use of this. But also inquiry-based learning, and this is a form of active learning which fosters curiosity and critical thinking skills, so it's very suited to science in general. And during inquiry-based learning, students will be poised with a question where they will seek to engage, explore, explain, elaborate, and evaluate their findings. And this, what I'm describing there, is the 5 E's of inquiry-based learning by Bybee and Landis of 1990. And this model is something I will use throughout my programme. Throughout the course, there are many different technology tools used from Zoom, Powtoon, Google Docs, Kahoot, and the bottom right there is a virtual Mollymod kit. And the reason I use such different technologies is simply to create a more collaborative space for students. I think using collaborative learning, and definitely in inquiry-based learning too, is very important as it helps engage the students and it helps to motivate them to move forward and also share ideas between them. So reflecting on the project design and development process, firstly, my thoughts on the design. I think the learning objectives are very suitable. They follow the A-level specification very well on the AQA examination board, and it's also very useful for students and for them to have a clear run-through which is organised. The learning assessments are very applicable and they match the examination questions which they will face frequently in the exam. The learning materials are very varied, and I think it also helps them adjust as they move forward into university. For example, having a guest lecture from a university setting will actually help the students a lot, and having them have a forum where they can talk to the guest lecturer and learn more on careers, I think it's very motivating for further study. And I think using an inquiry-based learning strategy is very suited to STEM subjects such as chemistry, for the collaboration point of view, critical thinking, and just exploring more curiosity within science and STEM. The use of the backward design model I think really suits this project, and I would use it again. It's been very easy to use from an instructor's point of view and designer's point of view, particularly on the fact that throughout it, each step I moved forward through the design model, I found myself evaluating what I had done, going back through the model and evaluating and tweaking again and making sure it all aligns throughout. So yes, I would definitely use the backward design model on future courses for chemistry. And here I have all the references I used throughout my whole course, which I found to be incredibly useful. And just now I'd like to say thank you for listening, and I hope you enjoyed it.